This is the first week of reading an introduction to statistical learning, and what I've learned, I've read chapter 2. So in essence, statistical learning refers to a set of approaches for estimating F. F, we almost never know what F actually is because it is invisible and unknown. F is invisible and unknown. So since we don't know this F, we are forced to build models, for example an F hat, to try and approximate it as closely as possible. So you might ask, why do we need to estimate F? We estimate it for either prediction or inference. In prediction, we are not concerned about the exact form of F, but the accuracy of the prediction. So we are mainly concerned about the output Y when we are estimating F for prediction. And on the other hand, in inference, it is almost the exact opposite. We want to understand exactly how the inputs are affecting the outcome. So we only care about the inputs and how it's affecting the outcome and the output. And you might ask, how do we estimate F, since we know how we can estimate it for either prediction and inference? For most statistical learning can be done in either parametric or non-parametric. In parametrics, it can be simplified as making assumptions. So you assume something about the F, something that you're trying to predict, like for the functional form of F. So you're trying to assume the assumptions of F. For example, we can assume that a model is linear. And in this example, you can see here, in every observation, it's not correctly fitting the observations. So it's just a straight line, and I assume that this thing is just a linear model. So this is like assumption. This is a parametric model. The disadvantage is the model we choose will usually not match the true unknown form of F. So it's just not the true form of F, just making assumptions. And if the model is too far from the true F, then our estimate will be poor. That is the parametric method. On the other hand, non-parametric method, it is also the exact opposite. So it does not make an explicit assumptions about the functional form of F. Instead, they seek an estimation. So they try to estimate it as closely as possible to the observations. The disadvantage is it needs a large number of observations. It needs a large number of data points so that to obtain an accurate estimate of F. For example, in this here, for this one, you can see the model is trying to fit into every observation. You can see the observation, unlike the linear model, it is not fitting everywhere. So this one is, for example, low flexibility, while this one is high flexibility. Flexibility meaning it is fitting on every observation. So why would we choose a more restrictive model rather than the flexible method? More restrictive meaning less flexible. Less flexible was the linear regression. Why would we be interested in a less flexible model than a very flexible model? If you are interested in inference, then restrictive models are much more interpretable. For instance, when inference is the goal, the linear model may be good choice since it will be quite easy to understand. This last is like a subset of linear regression, so you can just say linear regression here. This is the flexibility, and this is the interpretability. So this linear regression, it can be very easy to interpret. We've seen, and in this example, it is very easy to interpret, and it is very easy to plot. Unlike the other one, which is deep learning, it is very hard to interpret, very low interpretation, but it is deeply flexible. Assessing the model accuracy. In order to evaluate the performance, we need some way to measure how well its predictions actually they match the observed data. So we need to calculate if it is good, if it's doing good or bad, or the model is not doing very well. We have to some way measure it so that you can know if it's doing good or bad. For regression, the most commonly used is mean squared error, MSE. So y1, this is the actual value, and this one is the predicted value. So this one is for training data, and this right here, it shows how far the prediction is from the real response, and it is computed using training data, which is referred to as training MSE. But in real sense, we do not really care how well the model does on training MSE, but rather on the unseen test data. That is the test MSE. Let's look at this graph. Each circle is an observation, and the black curve is the real F. Even though we don't know what F actually is, this is just an assumption because the real F is unknown and invisible. These other curves, this one, the yellow one, is like a linear regression, and this one highly flexible because it's trying to fit in every observation. Training versus test MSE. Training MSE is the gray curve, and the test MSE is the red curve. Test, and the dashed line is the irreducible error. Irreducible error, this is something that you cannot be, it cannot be reduced to. You can never have a perfect model without the reducible error. We notice that the training MSE is bigger than the test MSE is bigger than training MSE. This is because more flexible models is better at test MSE till it reach a point. Increasing the model flexibility will result on the test data. You can see here, when you increase the flexibility, it will result on the test MSE here. Up to this point, if you try to increase the flexibility, it will just increase the MSE, so it will not do any good. So you're supposed to stop at a certain point so that you avoid overfitting, because this phenomenon is called overfitting. Okay, the bias variance trade-off. The bias variance trade-off. The U-shaped curve on the test MSE is a result of two properties. That is, variance of the unseen observation and bias of the unseen observation. This is the U-shape is caused by either variance of unseen observation and bias. We need to know what variance and bias is. To minimize the expected test MSE, we need a model that minimizes both variance and bias of the estimated F. If a model is too flexible, that will likely cause high variance. If a model is too flexible, that will cause high variance. And if a model is less flexible, bias will likely affect the data. That is the two main things that cause the U-shaped curve on the test MSE, the bias and the variance. On the other hand, we are supposed to look at qualitative or categorical data. To quantify the accuracy, we need, because since it's a categorical data, it's just words and all that, we need a way to quantify it. We need a way to measure it for the accuracy of estimating F. Now we use the training error rates. This is a training data. This is a training data, and this is the predicted category, and this is the actual value. For unseen data observation, we use XO and YO. This is what we use for classification setting.